Please join me in welcoming to the Distinctive Voices podium, Dr. David Keith.
Thank you very much. Thanks a whole lot. It's great to be here. It's great to have a good audience. I should say that I'm very tired and sleepy, so if I go asleep during my talk, you can wake me up, I guess. I've just been doing a few too many things. Let me unblank the screen here. So, in the middle of my talk, I'll say a fair amount technically about how these ideas of directly engineering the climate might work and answer some common objections people have about them. But before I do that, I want to spend a fair amount of time on some kind of background context, because people's judgment about whether or not these ideas make any sense, and in a second I'll say a little bit more about what the ideas are, turns out to be enormously dependent on the context. So if you think about engineering the planet by putting these reflective particles in the atmosphere as a way to cheap way to avoid cutting emissions and allowing us to go on with business as usual, then for many people that seems like a pretty bad thing. Whereas if you think of it as a way to limit risks to ecosystems and vulnerable populations, in addition to cutting emissions, then you typically think about it a different way. And that's just one example. There's a whole bunch of ways in which the way we frame these problems turned out to be probably more important than the actual technical answers. So I want to give you a little bit of kind of what my biases and background are, because I think it's pretty relevant in thinking about this problem as a whole. But so first, let me start with a really simple example of what we're talking about, what I'm talking about. So if you wanted to cut the rate of warming in half starting in 2020, you could, in principle, start with a couple of aircraft modified business jets, G650s, and you could do it from one base starting in 2020 and release some 10,000 tons of sulfur a year, that first year, into the atmosphere of sulfur. This would be to make fine particulates of sulfur in the upper atmosphere and the stratosphere. And they would reflect some sunlight back to space, and so partially cool the planet the same way as a thin cloud cools the Earth beneath. And in a sense, this is mimicking what's nature already does. So volcanoes cool the planet in a way that can be similar. But it's not natural. This would be a deliberate global scale intervention, or a deliberate attempt at kind of global scale partial control of the planet in a way humanity's never done before. So the amount of carbon dioxide in the atmosphere is going up as we keep burning more fossil fuels. So if that first year you had to put in, say, 20,000 tons or whatever it would be, next year you have to put in a little bit more and a little bit more. So after 50 years of that, by 2070, you'd need a fleet of probably a more advanced specialized aircraft, maybe 50 of them or so. And you'd be putting in a good fraction of 1 million tons a year of sulfate. And you'd be reflecting away something approaching a good fraction of 1% of the incoming sunlight. And you would have done, then for 50 years kind of slowed the rate of warming by roughly half. Of course, what happens after that is a lot of the problem that we'll get to. But that gives you a sense of it. You may think these ideas are completely nutty or good ideas, but I think an important statement that, from my point of view, is pretty much a statement of fact, is that they are technically doable. That's not a reason to do them, but it's important to understand that to try and think about how to manage these technologies. So the actual costs of developing this kind of hardware are quite well understood and not very large. Not very large, meaning kind of at the peak $1 billion a year class. And so for a 60 trillion global economy where the estimated costs of either the impacts of climate change or the cost of cutting emissions are kind of more like $1 trillion a year, this is a cost that's so tiny that cost isn't the deciding issue. The big issues are the risk of doing it and the risk of not doing it, all sorts of really hard questions about how we would control this thing, because this represents a kind of new unprecedented level of technological power. And controlling that power as a political problem is I think, a problem, I don't mean to sound hyperbolic, but a problem that's on the par with the controlling nuclear weapons. I mean, it's a very, very hard thing to do. And so I think really the political issues are harder fundamentally than the technical issues. But I want to give you a sense of what the kind of technical story was. Now let me say a little bit more in background about how I think about climate change, because I want to sort of give you some of my biases because they affect how we think about the whole problem. So I've worked actually now more like a quarter century, 25 years or so, on the climate problem. I take it very seriously. I have a kind of environmental background that's unusual, some family history of environmental activism, and also I've spent more time in the big wilderness than probably most people who don't kind of do active adventure for a lifestyle. So I've done, multi-week trips in the high Arctic many times. I think I've spent now about a year of my life outside. So I have more experience in that regard, and it means a lot to me. And I want to think explicitly about why we should protect the natural world for reasons other than pure utilitarianism. So it's become very common in debates nowadays to talk only about risks to people and to kind of sweep under the rug as sort of something we can't talk about directly, particular reasons that we might actually want to protect nature because we like it. I think the climate problem represents, by many measures, one of the largest environmental problems that we face, especially when you combine it with land use change over the next century. But I do not buy into the sort of catastrophic viewpoint that's become quite popular and become sort of quite salient in public debates about this. So folks like Jim Hansen, one of the most prominent kind of activists who's been very effective in raising concerns about climate change, concerns I share, has made comments like it's game over for the planet if we approve the Keystone Pipeline. I oppose the Keystone Pipeline, and that means a lot to me because I live in Calgary, Alberta, a good fraction of the time, whose economy depends on it. Or depends on the oil industry. But I don't think that these kind of catastrophic statements are true. And I also think they kind of dodge the problem. If it was really true that we faced a catastrophe, imagine an asteroid inbound for impact in 2050 that was a mass extinction creating asteroid. We would have no trouble getting political will together to collaborate to try and manage that problem. And because it would essentially be a forced choice. Climate change is not like that. Climate change poses real risks, but lots of other things pose risks too. And I think it doesn't have that kind of existential threat that means you must act in a kind of crisis way. Climate change, in fact, poses hard choices, and those choices depend on people's values and judgments. And there are plenty of people who think we shouldn't do much about climate change who are not stupid and are not necessarily climate deniers. So I think my view is you need to think more seriously about what the choices we face are. And in saying that, I also want to say a little bit about what I think of as catastrophic. So, because if I'm rejecting a catastrophic framing, I need to kind of give you a sense of what catastrophe means to me. So, first of all, I think by many measures, climate isn't even the top environmental problem if it's sort of a shorter time scale. Humanity, by releasing about 50 plus million tons of sulfur in the atmosphere from fossil fuel combustion globally, kills about 1 million people a year worldwide from air pollution. Even in North America today, that number is around 50,000. And I'm not quoting crazy numbers. These are numbers very well peer-reviewed, multiple independent studies from epidemiology. In fact, some of my colleagues at Harvard School of Public Health have been some of the leaders in doing that. There's a fair amount of uncertainty about exactly what number I should say. But there's no fundamental dispute about the sort of rough order of magnitude that air pollution is responsible, sulfate air pollution, for of order 1 million people a year globally. And when you poll people and ask them what environmental problems or risks they face, in North America, for example, many people will still say water, but the number of actual kind of measurable impacts or injuries of water pollution are tiny compared to air pollution. When I thought about taking the job at Harvard and moving from Calgary back here, I've lived here before, I, being a kind of nerdy guy, did the little calculation about what it takes off my life to live here, which is a lot more polluted than Calgary. And it's sort of order a year. The consequences of air pollution in a place like this take about a year off your life. I'm not making these numbers up. So I think it's important to kind of have a view. So if by environmental problem, you mean sort of risk to people, and often we use environment both to mean direct risk to people and environment to mean risks to the natural world. And in fact, these are very different things because we compare them to different things. So when I think about a health and environmental problem, by many objective measures, the leading one would be that. If you think about things that affect people globally, the leading issues are obviously poverty and disease among the poorest billion. But if you think about things that affect those of us who live in this area in a kind of direct way, affect our lives, alter how long we live, that are large-scale environmental things, air pollution really has to be number one. I also think that climate change doesn't pose an existential threat compared to what humans do to each other. So to be clear, humanity's done a much better job in the last century than in preceding centuries. This was probably, the last 100 years was about the least violent 100 years of human history in terms of the fraction of people that we killed by violence, but it's still a lot. And we do have weapons now that are still there that are able to kill enormous numbers of us very quickly. There's bases not too far from here where we make nuclear submarines that are, in a sense, the ultimate weapon that humanity's devised. They're still sailing around the ocean, ones that our country's made and ones that other countries have made. There was enormous effort to develop and weaponize biological weapons in Russia at the end of the Gorbachev era. Those technologies have not been forgotten. You can't uninvent them. Those things are real. So if I think about actually catastrophic threats to people over the next century, what I personally think about is the threat of other people. I mean, humans have immense technological power, including the technological powers I'm talking about, which can be used for war. And those, to me, are what I think of as catastrophic threats. So by that standard, I don't think of climate change as a catastrophic threat. I think it's a very serious environmental threat, and one that we can manage. There are hard choices about how we want to manage it. There are choices about how much we should spend to cut CO2 emissions, what other things we should do, what we should do to try and adapt to the risks of climate change, whether we should use these technologies I'll tell you about for engineering the planet. But those are choices that, in my view, are not forced choices. It's not like we have a catastrophe and we must act tomorrow or it's all over. And I think, and I'll come back to this a bit at the end of the talk, I think there's been a habit in some of the environmental community to, people are concerned, and I am very concerned, that we have largely, as a society, failed to do anything meaningful to cut emissions, to deal with the climate problem. I'm very disappointed about that. But the response of many of my colleagues, I feel, has been to turn up the volume, to say more and more loudly that it's game over. And I think that's not an effective response, because I don't think it's true. I think, in fact, we face these choices that are hard, but the way to deal with it is to actually begin to discuss really what the trade-offs are and be serious about what the costs are. So one last comment on that, and then I'll come really back quickly back to geoengineering. Of course, I've talked a little bit about exaggerations that you get on some of the kind of environmental activist side. There are plenty of exaggerations on the other side, maybe much more. So in the place where I spend a lot of my life right now, Calgary, Alberta, one of the centers of the oil town, people will routinely say that essentially it would be impossible to cut CO2 emissions, that it would mean the end of industrial civilization. That's nonsense. There's lots of ways, not ways at zero cost, but ways at cost that are still very low compared to, say, what we spend on healthcare, that we could use over, say, half a century in this country to drive emissions towards zero and still maintain roughly the same quality of life as we have, just by changing our energy system so it doesn't emit carbon dioxide. Some combination of solar power, nuclear power, wind power, better efficiency, these are things that are doable. So we can cut emissions. The issue is a choice of how much we spend to do it, how we rank that priority compared to other priorities. So I think there are two facts about climate change that are really important to know in thinking about this problem, and then I'll get on more to talk about geoengineering specifically. One is that carbon dioxide lasts in the atmosphere for a very long time. It is not like other pollutants that we've thought about. In some sense, it's not a pollutant. I'm not getting into that debate. But if you wanted to deal with that sulfur aerosol air pollution problem I told you about, and you could magically turn off all the sulfur-emitting machinery that we have strewn around the planet, it would take only a few days for most of that sulfate to be out of the atmosphere. If you keep increasing the amount of carbon emissions exponentially, as we've been doing, not quite exponentially in the last decades actually, and then you suddenly stopped, 1,000 years after you stopped, the warming signal would still be, half, a little more than half, in fact, of what the warming signal was at the peak. So it's very long. I have a slide I'm not showing you tonight because I didn't want to overdo some of these slides that points out that in many ways that's a longer lifespan than nuclear waste, which people think about as a very long lifespan. So that's a crucial thing to know. The second crucial thing to know is, well, you certainly can cut emissions. It's not easy. We can't cut emissions tomorrow. And those things matter because they tell you about what the choices we really face are. Because a natural reaction, and I think a very healthy reaction, when people like me talk about the possibility of these technological fixes, is to say, why should we do this technological fix? Shouldn't we just go ahead and cut emissions? And the answer is, first of all, cutting emissions only stops adding more carbon to the air. It doesn't deal with the carbon that's already in the air. So cutting emissions doesn't eliminate the risk the same way as cutting sulfur emissions would eliminate the sulfur air pollution risk. And you can't just cut emissions tomorrow. Well, you can do it over kind of a 50-year time scale. You can't do it tomorrow because of the way that these energy system is sort of embedded in the core of energizing our civilization, enabling us to travel and have illumination and computation and communications. So let me go ahead and I'll say a little bit more about what this system would look like and say a little bit about what its risks are. So very broadly, I'm talking about what's often now called solar geoengineering. So these are ideas of somehow deliberately engineering a way to make the Earth more reflective, to reduce the amount of sunlight it absorbs, to partially and imperfectly offset the risks of climate change. And in thinking about the risks of this, I think there's important to divide this into two very different categories. Don't worry, I'm not going to go through these in detail, but I realize I may have a little more technical stuff in this talk than I should have. But I think it is conceptually two very different things. One is to think about what the risks are of a particular way we do this. So as I'll mention later in the talk, I personally have worked a little bit on whether you could work on a certain kind of nanoparticle that might be better for doing this, might have less environmental risk, but also it might have more environmental risk. We don't know well enough. So the point is there are particular ways you might do it that have risks particular to the way you reflect away the sunlight. And those things to me are particular to the system, and they're risks that are kind of separate from the main effect you're trying to have, which is reduce the amount of sunlight. So there's a bunch of risks, like, for instance, acid rain from adding a sulfur to the stratosphere. That turns out to be pretty much a non-problem because you're only adding 1 megaton a year. We're already adding 50, and it's evenly spread. So when you do the math, it turns out to be a non-problem, but you got to think about it. There's a bunch of potential risks. Then there's things which I would call the efficacy. So if you warm the climate, change the climate by adding carbon dioxide, and then you turn down the amount of sun, even if you did it in a way that was sort of clean or perfect by some space-based shield that just magically reflected away 1% of the sunlight without causing any local pollution or change the ozone layer or anything. Even if you do that, you cannot compensate for all the climate change you've caused by CO2 because the things that CO2 does to the climate, which include geochemical things like changing the acidity of the ocean, are just not the same as reducing sunlight. Reducing sunlight is not anti-CO2. So it does appear to be, that reducing the sunlight by this little amount could actually significantly reduce the risks from carbon dioxide, but it does not counteract them perfectly. It's inherently imperfect. So there are a bunch of things you can figure out about the efficacy, basically effectiveness in reducing risks you care about, like risks to crop loss or risks of heat stress or risks of ice sheets melting. And you can study those and try and understand the extent to which these techniques could reduce the risks. And so I would call that efficacy, and that's true even if you had a sort of imaginary perfect way to reduce the amount of sunlight. An obvious question you might have is, say, does the direct reduction of sunlight matter much? And the answer is, like for crop productivity. That answer turns out to be no, but it's a good question to ask. So I'm going to first say a little bit about a couple kind of technical ideas, which maybe will be interesting to those of you who want them, but also give you a sense of how little has been done here. So the underlying idea that this was possible turns out to be very old. So the first real report that had any kind of modern understanding of climate science that went to a US president was a report that went to President Johnson in 1965. And it has basically the core climate science all correct. It's very well written, too. And that report, in fact, proposed only one thing to do about it, really, which was a variant of these techniques. So these ideas are not new, but there was a taboo against talking about them for a long time. So there was effectively an agreement among the scientific community that we wouldn't talk about it. And I think the underlying reason was that the fear that if we talked about it, people would lose their incentive to cut emissions, which has now been, I think, incorrectly called a moral hazard. So as a consequence, there's been very little sort of serious scientific attention paid to this topic. And I'll just give you one little example. So I mentioned volcanoes, and volcanoes certainly do cool the climate, and pretty much everybody had assumed, and a whole series of papers and analysis on this has sort of assumed that you just copy volcanoes. Volcanoes put sulfur dioxide in the stratosphere. Well, it turns out not to be so simple. So the effectiveness of a little particle in cooling the planet, a little particle in the stratosphere, turns out to depend very strongly on how big it is. So if a particle was big, it would just fall right out of the stratosphere right away. So only very fine particles can stay there for a long time. So this is the size of the particles. Particles that are bigger fall a lot faster. They fall kilometers a year and fall out of the stratosphere very quickly. Another fact is that particles need to be a certain size, some fraction of a wavelength of light, quarter of a wavelength or so, in order to be most efficient at scattering light. Very big particles aren't very efficient at scattering light per unit of size, per unit of mass. So those two factors mean that you really want the particles to be very fine. If you just do what volcanoes do and put SO2 in the atmosphere, it turns out almost all that SO2 ends up going to the existing particles, which get bigger and bigger. And so you have a very ineffective way to cool the planet. So this is some measure of sulfur injection in millions of tons a year. It's 20 at the top here. And the standard assumption had been that this would be linear, so that this is the amount you're cooling the planet from 0 to 4 watts per square meter, which is roughly like 2 times CO2. The standard assumption had always been that you could just walk down that line, and it would take a very small amount of sulfate, a few million tons a year. Well, whether that's small or big is a value judgment, but that kind of amount in order to offset the effects of doubling CO2, which, by the way, I don't think makes sense. I'll get to that later. But it turns out that that doesn't work. That, in fact, you end up just making bigger and bigger droplets. And some of our colleagues figured this out, and then I and some others, we put together a team of people between Zurich and Carnegie Mellon and Harvard, and we figured out a way that might work, untested, to manage this problem. And that way is that if you release sulfuric acid directly from an aircraft to the stratosphere, it turns out you tend to make very fine particles. Instead of releasing sulfuric SO2, which takes about a month to turn into sulfuric acid by oxidation. So this was sort of the result that we'd get if these sort of asymptoting, where you just put more and more sulfur in and get less and less of a radiative effect. That was the result if you just put SO2 in the stratosphere. But if you put sulfuric acid in the form of, well, not as droplets, just as a vapor, but the vapor makes droplets very quickly, you can get something that gets you much back to sort of the original theory. So that's an example. It's not a particularly hard thing to do. Whether it actually works or not, we have no idea. You'd have to really do tests. But it's an example of essentially how fresh the science is. It's sort of easy to publish papers like this because people just haven't looked at it very carefully. And so that's a big caution that I want to say now, and I'll say it again at the end. So I'm somebody who's advocated that we take this seriously. We think about it hard, and we have a research program. And in many ways, I advocate, developing the capability to do it. But if you ask me now, should we do it today? My answer would be absolutely no, because I believe there's a real risk at this point of sort of scientific groupthink. There's a pretty small group of scientists, of whom I'm one, who are kind of been the leaders of doing research on this, and there's a clear groupthink danger. And I think before I, as a citizen, would vote to move forward with these techniques, I think we have to broaden that scientific debate out a lot and have a much more of a kind of what the military calls a red team, blue team exercise, where we have groups of scientists who are trying to figure out how to make it work, and other groups trying to figure out all the ways it's going to go wrong. So I'll say, I'll actually skip the next slide and say a little bit more technically, but I want to really go through a bunch of very common concerns and give you some ideas about some of the technical answers to those concerns. And then in the latter part of the talk, I'll tell you what my concerns are, which actually aren't the same as a bunch of these common concerns. So I have some quite strong concerns about the way these technologies could be misused. But there's a bunch of very standard concerns people raise, that this is highly unequal, that it can't be tested except at full scale, that you can't control systems you don't understand, that you're committed to do it forever once you start, and that it's kind of a Band-Aid that doesn't deal with the root problems. And I want to kind of, not any of these are perfectly answered. Some of these are quite legitimate concerns. There's useful things to say, but I want to give you some sense of why, despite those concerns, I and many others now take quite seriously the idea that we should think hard about this. So I'll do that one by one, and then come to what some of my concerns are, and then close. First of all, inequality. So this is a quote from a paper by Alan Robach, a real expert on volcanoes and stratosphere. quote from a paper of Alan Robock's in 2008, and that turns out to have just spread around the blogosphere. So if you Google geoengineering and volcanoes, this is something like half of all the references mention this thing about Asian monsoons. And there's an enormous amount of people in the kind of social science and political world who say that this is sort of rich world scientists who for profit want to keep the existing system going, and it's going to shut down the monsoon. And there's all sorts of places where you can find confident statements in published scientific papers that say this is true. Well, it doesn't actually appear to be true, or it's only true with some very particular settings of the climate model knob. And so I'll give you some sense of that. But first of all, I want to talk more in a more basic way about inequality that's more systematic. So I said before that things you do to warm up the planet by adding carbon dioxide, that we are doing by adding carbon dioxide, cannot be perfectly compensated for by reducing the amount of sunlight. So to sort of think of that conceptually, imagine that I have two regions. This could be U.S. West Coast and U.S. East Coast, or it could be Indian precipitation, Indian rainfall, and Chinese temperature. Just take two variables in the Earth's climate. So I'll call one of these variables region A. Maybe this is the East Coast of the U.S., and one region B is the West Coast. So when I turn up the amount of carbon dioxide in a climate model, anyway, you can do this, and in the real world we are, of course, doing it, is you'll have some way in which both regions warm, but they won't warm exactly the same amount. So in this particular diagram, region A is warming a little more than region B as we turn up the amount of CO2. So solar geoengineering, we hope, kind of goes the opposite direction. It makes both sides cooler, but it also won't be exactly equal, and the two won't be equal and opposite. And the question really comes down to, if you remember vectors from high school, how aligned these vectors are. So we can't just choose how long this vector is. This is the amount of carbon in the atmosphere. It'd be great if we could just choose and say, okay, we're going to have that back to 0, but that's this enormous inertia. That's the vector that comes from us adding carbon dioxide, and it's very hard to get it out. But we could, in principle, choose how long this vector is. This is how much sulfate we're adding to the atmosphere, because the sulfate is cheap to add. There are all sorts of problems, but the expense isn't going to stop you, and it doesn't last very long. So you could adjust. I mean, how we decide politically how much to do is the hard part, but in principle, there's technically no reason you can't decide how long this vector is going to be. And if you have this amount of warming and this amount of cooling, this is the residual. So the question is, does it look like that? This is just a fun drawing. It's not based on science yet, based on any actual calculations. So if you had this inequality, in principle, you could choose this to be long enough to make this region exactly where it was before, but leave this region a little bit too warm. Or you could make some equality. So the question really is, what is the trade-off between those regions? But again, I just drew this diagram. The real question is, what is the angle, if you like, between these two vectors? So if the angle was, if they were exactly equal and opposite, then you'd say that in a climate model, this solar geoengineering was perfect, that it exactly compensated for CO2. If the vector was more like 90 degrees, you'd say, well, it just makes another climate change, but actually doesn't help at all. Doesn't reduce the net effect. And so the objective question is, thinking about inequality, what is that angle? And people had done all sorts of papers or references that kind of cherry-picked individual places. But some students and I decided to be a little more systematic and actually take these 22 standard regions that are widely used in climate impact analysis and think about this in a kind of systematic way without choosing which region we cared about. So these were the standard regions, so the Tibetan Plateau or southern South America, what have you. And in these units which are normalized by the interannual change, so this isn't actual temperature units here. What the blue curve shows you is, blue line shows you what happens to temperature if you doubled CO2. We're at the time of CO2 doubling in a model where the carbon is ramping up. And you see pretty much every region gets warmer. Precipitation, rainfall is different. Some regions get wetter, some regions get drier. And the red lines show what happened when you do a certain amount of SRM, or of solar radiation management. So this gives you a sense of what the trade-offs might be by regions. And this may be, for some of you, will seem obvious, for some less, seems abstract, but if I've got these 22 regions, I can think about this as a 44-dimensional space, because I've got temperature and precipitation in 22 regions, and I can still think in terms of vectors. It's harder to visualize, and ask myself, how aligned are those vectors, which basically is, how good a job does it work? How good a job, how well does it compensate? And I found the answer surprising. When I started writing the paper, I was thinking we'd show that it didn't compensate very well. I mean, the picture I had in my head was about like that it would sort of, compensate for about half of the effect. The result, at least from this model, but actually there's now another paper under review that shows this for a whole suite of climate models, all of them, and it shows basically the same number. The result was that if you choose the amount of geoengineering, for example, to minimize changes in precipitation, you can cut the change in precipitation kind of, the average change in precipitation across all the regions by 87%. So you basically make almost all the change in precip go away. So that you can make it so that the 2030s precipitation is within 17% of the original. That's stunning. I mean, there's people many papers out there says this doesn't even help for precipitation. And in fact, what we find is that on a region by region basis, it actually is, I think, kind of amazingly close to perfect. I am not saying overall that geoengineering is close to perfect in a large picture, but in terms of just the basic question of what the response of climate models look like, it's much more equal than you might think. Perfectly equal? No. Am I saying that it, and to be clear, concerns about inequality are extremely relevant. So I'm not sort of poo-pooing these concerns, but actual measurements from climate models, the same climate models we use to talk about the risks in the first place, show that the inequality concerns are not maybe so big. Second thing is, it's commonly said that you cannot test this without full-scale implementation. So it's not a robot quote, but many people have said different versions of this. And I just don't get it. Part of it depends on what you mean by test. So there's laboratory tests. Then there's what atmospheric scientists call process experiments. These are experiments where we try to understand how one thing in the atmosphere alters another. So maybe how the size of cloud droplets changes how white a cloud is. And then there's questions about the whole atmosphere's response. So it's certainly true that you cannot test the whole atmosphere's response without actually effectively doing it. Although you don't have to do it at full scale. It turns out to be there's nothing magic about that when you think about signal or noise. But there's lots of process experiments you could do that look at particular risks. And I'll show you one that my colleague Jim Anderson and I are working on to give you a sense that this is real. So I'm not going to go into this in detail, but the point is we're preparing the design of an experiment that would release tiny quantities, less than a kilogram of sulfur in a small region of the stratosphere. This would be a region that would be no more than kind of 100 meters on a side that you'd look at to measure specific things about ozone chemistry. So there's specific ways in which these chemicals might destroy ozone, and we can test models of ozone destruction by doing a controlled perturbation. The amount of sulfur we're emitting is tiny by almost any reasonable measure. So our goal is to make a perturbation as small as possible in a well-mixed volume so we can measure the kind of key technical scientific question, which is how ozone loss depends on water vapor concentration, as it turns out, and also on sulfate aerosol concentration. And so there's a whole mass of experimental design work over the last year that's got us these numbers, but right now we think we're quite a bit less than a kilogram of sulfur that we need and less than 100 kilos of water. So that's equivalent to sort of a minute of a regular commercial aircraft flight. So I think it's fair to say the objective risk of this experiment is very small, since it's kind of similar to a minute of a commercial aircraft flight in the stratosphere. And there's no question we will learn something useful that helps us quantify the risks of large-scale injection of sulfate or other particles if we did them. Does that mean we answer all questions? No. Does it mean we can, a whole series of these experiments could tell you everything you want to know and eliminate uncertainty? Of course not. The uncertainty will always be large. But statements that you can sort of only try it by doing it at full scale, I don't think are supportable. There's some little picture that gives you a sense of what we're doing. I won't go into the details. Here's another that is often said, and this sort of makes intuitive sense to a lot of people. They say, well, we don't understand the climate system, so how could we possibly control it? The answer is we routinely control systems we don't understand with feedback. All sorts of engineering systems all around the planet use these techniques. It's inherently imperfect. You can never do perfect control of a system you don't understand, but feedback allows you lots of control of systems that you don't understand very well. Here's a very old slide I wrote about this, and then I'll actually show you some new research on this topic. So a kind of intuition, chaos means extreme sensitivity to initial conditions. And so people have the idea that the atmosphere is chaotic, and in part it is. Weather's chaotic anyway. So you might assume that control was impossible. Not so at all. There's all sorts of cases where we do deliberate control of chaotic systems. So what you need is a model of the system. You need some observations of where the system is at a given time. And you need an appropriate lever, a way to manipulate the system, and you need feedback. Basically, if you keep watching what's happening and adjusting as you go, you don't have to have a perfect model. So it's one thing to say that you have to choose exactly how much geoengineering you do now and not change your mind for 100 years. That's equivalent to no feedback. So take whatever knowledge we have of the atmosphere now, aim for 100 years, close your eyes and hope. That would be no feedback. But there's no reason we have to do that. We're going to keep observing. We're going to do a little bit and watch what happens, do a little bit more, watch what happens, watch the atmosphere's response, and continuously adjust. And with feedback, you can easily control chaotic systems. And sometimes you even want to have feedback. So this is an aircraft that was deliberately designed to be unstable because it turns out once you have what we call closed-loop control with feedback, you can do a better job controlling the aircraft, have more control authority, as they'd say, when you have feedback than when you don't. So basically improved observations, improved models, and improved analysis or forecast systems all give you the more ability to control. There's a point here I want to emphasize. So whether or not you like the idea of our ability to kind of control climate and weather, whether or not you do any research directed at that end, the increasing power of the observational systems that are happening for other reasons, the increasing quality of the models, the improved analysis forecast systems is making it every year incrementally easier to do these kind of controls because they give you the ingredients you need for feedback. Here's some specific examples. So this is a nice feedback diagram for people who are used to them, but let's just say that we actually have tried this out by taking 2 climate models and a very simple model, and we've developed feedback controls for the simple model, and we've calibrated them off one climate model, and then applied them to the other, kind of pretending that we didn't know about that second climate model. That we can't do it on a spare Earth, but at least we can do it with 2 climate models and say, let's say we had our feedback tuned up for one, and we applied it to the one where it was not quite right. How well would it work? And the answer is it works pretty well. And like lots of things in this thing, you always, in this topic and many others, you always find trade-offs. So when you apply feedback, you can more or less make the system work. Here's where we're trying to control in a model land average precipitation, and we start in 2040, and we can make the precipitation do closer to what we want. But it's still not perfect. There's still lots of noise. And indeed, it turns out, and there's some theorem that has a nice name, the waterbed theorem in control theory, that says that in fact, if you make it better in one way, in one frequency band, as control theory people say, you end up making it worse in some other way. So we actually make some of the high frequency variability of precipitation a little bit worse by doing feedback than if we didn't. And that's one of the many ways in which there's no free lunch. And that's actually a robust result, impossible to get out of. But the statement, the sort of simple statement of Ron Prin, who by the way is a wonderful and thoughtful guy, that you can't control a system you don't understand is just wrong. That's just people are, his mental model is that you're doing a one-time decision with no feedback. And that isn't what we'd actually do. I'm going to skip over it. Skip over these next ones, but we've also looked at whether non-uniform forcing could do better feedback. And the bottom line of this, just to say, is that you don't have to do the dumbest geoengineering where you just do it everywhere. You could imagine tuning a little bit. So for example, you focus most of the effort on reducing or restoring sea ice in the Arctic without doing very much to change temperature, precipitation in the tropics at all. So we've looked at whether you could do that in a suite of climate models, and the answer appears to be yes. So while uniform solar forcing affects everywhere, you can, it's pretty obvious what you do. You don't really need a climate model to find out. If you tend to do more of your sunlight reflection in the northern hemisphere summer, which is just when the ice is melting, you can have a quite big effect on restoring sea ice in climate models, but there's every reason to believe it will be true in reality as well, with a pretty small average forcing. And so we've looked at that. We've also found you can reduce inequality, the residual inequality, quite a lot using these feedback methods. A lot of this work was all done by Doug McMartin, who is a control theory expert from the Caltech Dynamical Control Group, who I kind of encouraged into this field, and we published a bunch of papers together. Another very common statement is that once we do it, we have to do it forever. And there's all sorts of variants of the statement. So people will say, doing geoengineering means that you have more CO2. And what they really mean is they're really thinking about feedback in the human system. They're thinking about that if we do this, people will lose their effort to cut emissions, and emissions will be higher than they otherwise would be, and so things will be worse. I think that is a sort of fundamental confusion of cause and effect. The environmental damage is being caused by the CO2 emissions. That's the thing for which we bear a moral responsibility, for which we are passing on real risk to our grandchildren, completely independent of whether or not geoengineering works. There's no way out of the basic fact that if you put more CO2 in the air, we are taking advantage of cheap energy today and passing on a risk to our great-grandkids. We can argue exactly how big those risks are, but there's no escaping that basic fact. And nothing about geoengineering changes that. Geoengineering may or may not reduce the risks over the next 50 years, but it doesn't work forever. But this idea that we have to do it forever when we start is just nuts from my point of view, to be blunt. I think it's supposing an all or nothing view of geoengineering. It's supposing that the way you do it is you do it enough to compensate for all of the changes due to CO2, and there's lots of papers that assume that, and that you then let emissions go on unabated forever. That would definitely be a dumb plan. But nobody's suggesting that plan. So it's sort of a straw dog to attack. Here's a plan that I'm actually suggesting to you tonight. So there's this thing that's widely used by the Intergovernmental Panel on Climate Change called RCP 4.5, which is an amount of radiative forcing, basically the amount of CO2 in the air that's estimated or projected over the next 150 years. That's the sort of standard blue line. And I should say, this is a scenario which has an extremely fast decarbonization of the energy system, much faster than has actually been achieved to date, and fast compared to historical energy transitions. So this is not business as usual. This is a sort of great outcome where we really do a good job cutting emissions. This is this line. So we've been playing around with sort of just scenarios. We're not trying to be optimal. We're just trying to be less stupid. We've been trying around for scenarios of what sorts of geoengineering pathways might make some sense. So one of the scenarios is that you divide the rate of change in half. So you choose the amount of geoengineering you're doing to make the rate of change here half as big. That's arbitrary. I'm not saying half is necessarily the right number, but it's a good guess. I'll come back to why. So this curve shows you the amount of geoengineering we're doing under this scenario, where it peaks at around 2060, and it goes back down. It's not forever. And it is certainly true that this scenario does absolutely nothing to reduce climate change, say, 3 centuries out. Geoengineering is inherently short-term, and that's good or bad. The effects of the cooling are short-term. Also, if you don't like it and want to stop, some of the residual effects will be relatively short-term. So it's absolutely true that the very long-term impacts of CO2 aren't controlled by short-term geoengineering. But there's a tendency in some of the geophysics community to think that all that matters is these effects 1,000 years out. But there are actually generations of human beings alive today who will be impacted by the CO2 we have in the air from, say, crop losses. And there is no question that doing this would meaningfully reduce the risk. Now, there may be other risks that it makes worse. I'm not saying overall it's the right thing, but it does reduce risks, and it's quite significant. So you might think that this difference was small, but it turns out that people don't know exactly how to think about climate risks. Indeed, there are many different kinds of climate risks, and they're all different, but lots of them depend on the rate of change. And some of them are more like the square of the amount. So if you have twice as much climate change, you have 4 times as much damage in many cases. Depends on what thing you're talking about. But even something like this that makes a very relatively small difference when you kind of look at it from way back, significantly reduces climate change risks if you look at, say, standard models of crop losses. Doesn't fix the problem, doesn't make the problem go away, but again, nobody responsible is saying that this will do that. It's saying that it could reduce the risks. Finally, there's this kind of common comment, this really isn't a scientific one, that this is a Band-Aid that doesn't deal with the root problem. And I think the short answer is yes. But that's not a reason for outlawing Band-Aids. So there are lots of places where we have, and I guess I should wrap up soon, I said it before 5 minutes. There are lots of places where we have behavioral feedbacks that mean that risks aren't reduced as much as you think when you make technical changes. So if you make cars much safer and put seatbelts on, people drive faster. If you give people drugs to prevent AIDS transmission, people have more risky sex. There's a whole bunch of these examples. They're well understood, and in many respects, they are rational. If you get pleasure out of some kind of risky activity, and you're balancing that pleasure against your risk, and you have some technological fix that reduces the risk a little bit, it's rational to do more of the behavior. It's not dumb. So I do a lot of climbing and mountaineering, and I take more risks when I do have a satellite phone or some way out than when I don't. That's not dumb, it's a choice. So the idea that somehow we shouldn't do things because they're Band-Aids, I mean, the extreme version of that would be, well, maybe we should take away safety procedures we have, like safeties in aircraft and cars, so as to make more risk, and then there'll be behavior correction the other way. That doesn't make sense. And then the other issue is, what the heck is a root cause anyway? So this is a comment from one of the groups that have been most strongly opposed to geoengineering and call people like me geoengineering profiteers. But I just want to get you to think a little bit about that. So they're sort of assuming here the root cause is the level of CO2 in the atmosphere. That's an assumption. You can't say it's right or wrong. Slowing down or stopping the transmission of flu virus does nothing to change the rate at which new flu strains arise. Actually, it might not be quite true from contact with poultry. Slowing down or stopping CO2 emissions using industrial scale wind power does nothing to change the control of the energy industry by corporations. Slowing down or stopping the rate of warming via solar radiation management does nothing to change the factors which drive our species and limit of its carrying capacity, the sort of social factors. The point here is that there's no magic answer about what the right cause, the sort of root cause is. There's no kind of stopping rule. So if it's convenient for you to argue that the root cause is CO2 in the atmosphere, then most certainly solar radiation will not help. But if your concern is risks from climate change, then it will help. So this is all about framing. So I don't want to sweep this under the rug. There certainly are very basic ways in which this does not deal with the root problem. But that isn't in itself an argument for ignoring it. So that's a review of some of those. I'm going to try and now speed up a little bit and tell you what my fears are. My biggest fear is we don't live in a world with a single kind of magic global impartial actor. So I would say the following. If we lived in a world in which we had some kind of effective global democracy and some committee of considered people who were legitimately drawn from around the world, who could put up their feet and analyze this carefully and make decisions in our best interest, and then could act in this kind of incremental way I talked about, where they wouldn't just do it at, canceling out 2 times CO2, but they do it slowly, and they'd also be cutting emissions at the same time. If we had a committee like that, my view is that there is the overwhelming scientific evidence to date that doing some amount of solar geoengineering would reduce risks and would be a wise thing to do from what we know now. We may learn more that changes my mind, but that's what I think now. But of course, this is a kind of irrelevant hypothetical. We don't live in a world remotely like this. The real world we live in, it's extraordinarily hard to coordinate actions between countries because of the sort of public goods problem, as economists call it, even if countries broadly agree about what the right answer is. So to me, the fundamental risk here is about conflict right up to war. These technologies are extraordinarily high leverage in the same sense as nuclear weapons are. So in the same sense as there's like a factor of 10 to the 7 or so, between 7 and 10 to the 8, so 100 million kind of scale factor between the explosive power of conventional explosives and nuclear explosives. Same kind of ratio here. A couple grams of sulfur in the stratosphere offsets the radiative forcing of a ton of carbon dioxide in the atmosphere. That's an enormous leverage. It gives you enormous kind of power over the planet. And that physical fact is the underlying reason why this is cheap. Cheap isn't necessarily good. That means there's an enormous potential for unilateral action. That means essentially, very small countries could do this, non-countries. And I think the combination of this high leverage, the fact that it acts quickly, the fact that there certainly is some inequality. I didn't mean to say there was none. I just meant to say it's not as bad as people assume. And it means increased likelihood of conflict, or at least there's a real risk of that. So to me, I'd say broadly, my big fears here are not about the kind of direct rational risks of geoengineering. They're about the way it will be used in the political system we actually have. I have some concerns about what it's used for. I think mostly about using this technology as a way to reduce the climate change risks. But once you invent the technology, people may use it for completely different things than the original inventors intended. So here's a beautiful quote from the 1982 National Academy report, and I've talked to Tom Schelling, and I know that he wrote these words. And he says, interest in CO2 may generate or reinforce a lasting interest in national or international means of climate and weather modification. And once generated, that interest may flourish independent of what is done about CO2. So I and most of the other people working on this are thinking about this as a way to reduce the CO2 risk while we also cut emissions. But you can just think of this as a way to manipulate the climate to achieve all sorts of ends. So if you wanted to maximize global productivity of ecosystems globally, you might well want to have more CO2 and then do some specially tailored geoengineering. And there's ways that it's not hard to think about that you could do that likely would increase global crop productivity. I'm not advocating that, but once you invent these things, people will, that's a value choice what you use it for. And I do think this is real, that as you go down this road, people will start to just thinking about, what is the right answer for the climate we want, which is not, what nature gave us. And in a sense, there's nothing unusual about that. I mean, we spent the last 10,000 years trying to, inventing agriculture and shaping a bunch of the surface of the planet in ways that suit our interests. So it's not unusual for humans to do that, but I have concerns about doing it quickly. There's this kind of easy out moral hazard thing, which, while I partly dismissed, I don't want to wish away. I think there will be behavioral compensation. If these technologies are used, I think it's quite likely that it will mean that people cut emissions less than they otherwise would have. The chain is simple. That's the basic chain, and that's the worry. Now, it's not clear-cut. It's possible there's the opposite reaction. It's possible that people will sort of say, well, if pointy heads like me or more serious ones maybe are actually proposing these things, then we should take the climate problem more seriously and really act. And there's some actual evidence from some polling that this is true, but I think it won't end up being true. Much better than my slide is this. I just love this. So he says, the search for a breakthrough technology to solve the climate change continues, and this guy says it's a time machine that'll take us back 50 years to when we should have put a tax on carbon. And the punchline in these Tom Tolles cartoons is always at the end. This little guy says, well, we better hurry then. And then the guy right at the bottom says, no, that's the great thing about this technology. It's a time machine, you don't have to hurry. And I think that is pretty much the concern here. And I think it's real. I mean, there is some respect with respect to sort of radiative force in the atmosphere that this is the time machine we're inventing. And then there's all the actual side effects and risks, which I don't think are not dismissible. They're real, but my sense is that for lots of them, there are potential ways around them. And when you look at them quantitatively, they're not so big compared to the benefits, at least as we know them now. So I guess what I'm saying is, from my own point of view, the kind of narrow technical risks seem to be less crucial than some of these big ones. But that's my value judgment. Finally, last slide, a really beautiful quote that I think is thoughtful from Freeman Dyson that said that, well, you can read it. Thank you very much.